Welcome to my channel Sharath NEET Academy. In this video we are going to discuss about the concept of velocity selector. Before going to start this, we need to understand the concept of crossed field. Crossed field means we are going to apply magnetic field and electric field simultaneously, but crossed field means electric field and magnetic fields are mutually perpendicular. Then only we can call it as crossed fields. In the previous video we have seen Lorentz force. Lorentz force is a combined force of both magnetic and electric forces. So there we have applied in some cases electric field and magnetic field, both are in the same direction. But in crossed fields we are going to represent electric field and magnetic field are mutually perpendicular. Okay. So we know how to deal with the magnetic force and how to deal with the electric force in the previous video. Magnetic force can be known by using Fleming's left hand rule. Electric force direction can be known by knowing two statements. Positive charge experiences force in the direction of electric field. Negative charge experiences opposite to the direction of electric field. That's it. It's a simple. Whenever charge is there, external field is there, irrespective of angle of projection, electric force will act. Okay. But whereas magnetic field, in two cases it will be 0. Theta is 0 and theta 180. Then magnetic force is 0. In all other cases, magnetic force will act. Magnetic force acts as a centripetal force. It used only to change the direction of the charged particle. It never increases the speed of the charged particle. These things we have to keep it in our mind. Now, in this velocity selector, what we are going to do? We are going to apply electric field and magnetic fields are perpendicular to velocity of the charged particle. That means electric field, magnetic field and velocity of the charged particle all are mutually perpendicular. All are perpendicular. Then what will happen? We'll see in this case clearly. See here I am going to project a positively charged particle along the x-axis. Along the x-axis. That means velocity vector v is equal to v naught into I cap. Velocity vector. Okay. This velocity is v. Okay. Now electric field I am going to apply in the direction of y-axis. So that means electric field vector E bar can be written as E naught into j cap. Okay. The magnetic field I am going to apply along the positive z-axis. Positive z-axis is going to represent on the board like this. This is the magnetic field. So the magnetic field B bar is equal to B naught into K cap. This is how the electric field and magnetic field and velocity of the charged particles are mutually perpendicular. Now, we are going to study individual effects. First, you imagine I have switched off the magnetic field. Magnetic field is not there. Magnetic field illa. Bare electric field ide. Electric field is on. Then electric force, see charged particle is moving in this direction. This charged particle produces electric field and magnetic field. Electric field of the charged particle, applied electric field will interact. They'll exert force. Electrostatic force always acts in the direction of electric field for positive charge. That means electric force will act in this direction. Electric force. So electric acceleration will be in this direction. Electric acceleration is QE by M. Electric acceleration is QE by M. Okay. So force acts on this charged particle in this direction. Velocity is there in this direction. So if the charged particle moves, it moves in a parabolic path. Like this. Because initially velocity is more in this side. So more x distance rather than more y distance. Y distance is less initially. X distance is more initially. As the time goes, this velocity remains the same. because there is no acceleration along this component, there is no force along this component, this velocity remains the same, this velocity initially 0, this value goes on increases, at certain time this velocity becomes equal, after that its velocity is more, so later y displacement is more, x displacement is less. This we are going to represent like this. Is that clear? Only electric field is there, electric force will act in this direction, so the charged particle deflects like this. Okay, now I know electric force is QE along the y-axis. Electric force is QE into J cap. Now forget about electric field. Electric field is not there. Now electric field is switched off. Electric field na now off ಮಾಡಿದೀವಿ. Magnetic field na on ಮಾಡ್ತಾ ಇದೀವಿ. We are going to switch on magnetic field. See, magnetic field is in this direction. Magnetic field is in this direction. Charged particle is moving in this direction. Charged particle is going to produce electric field and magnetic field. Now we have applied only magnetic field. Magnetic field and magnetic field will interact. Two electric fields are not there. Only this electric field is there. This electric field is not there. So there is no electric force. Only magnetic force. That magnetic force, how it will act, we'll see. See the charged particle. Magnetic field is in this direction. Magnetic field is in this direction. Charged particle is going in this direction. Positive charge. Direction of positive charge, current, both are same. So I have to turn my finger like this. Field is in this direction. Current is in this direction. So force will act downward. So here magnetic force acts downward. When there is no electric field, there is no electric force. Only magnetic field is applied, only magnetic force will act. Magnetic field and velocity of the charged particle is perpendicular. So it traces a circular path. It traces a circular path like this. This charged particle makes a circular path like this. So if magnetic force acts towards the center of the circular path. Okay. Here magnetic force is acting towards the center. Acceleration will be there in this direction. Acceleration along this again 0. So this velocity, this speed remains the same. So that's why radius of the circular path is same. Radius of the circular path is mv by qb. Velocity, speed of the charged particle is not changing. Velocity is changing because direction is changing. So radius remains the same. So when we apply a lone magnetic field, this charged particle is rotating in this direction. Magnetic field is out of the plane of the board. Out of the plane of the board. Positive charge is moving in clockwise direction. Charged particle is moving in a clockwise direction with constant radius. With constant radius. Okay. If it is only electric field, parabola. If it is only magnetic field, circular path in clockwise direction. If I apply simultaneously both electric field and magnetic field, ನಾನು ಎರಡು fields apply ಮಾಡಿದೀನಿ. ಆವಾಗ see magnetic force I'll write here, F magnetic is QVB magnitude, but force is acting along the negative z axis. Sorry, magnetic force is acting along the negative y axis, so that's why it can be represented with minus j cap. If I apply Lorentz force, F bar is equal to QVB into minus j cap plus QE into plus j cap. This is Lorentz force. Now see here, fortunately electric force and magnetic forces are acting in opposite direction. So I may have three cases here. Case 1, electric force is greater than magnetic force. Then net force, net Lorentz force is only electric force with less magnitude. For example, electric field force is 10 Newton, magnetic force is 8 Newton, then answer is only 2 Newton, that too electric force, that is electric force. So when only electric force, this 8 Newton of magnetic force is cancelled by 8 Newton of electric force, so 2 Newton electric force is left. That's why now, even though I have applied electric field and magnetic field, only electric effect will exist on the charged particle. So that's why it moves in a parabola. But this parabola will come like this. Parabola path will different. Okay? Right. Next case, for example, if electric force is equal to magnetic force, both are equal, both are equal. In this case, what will happen? Electric field force nullifies magnetic field force. That means even though we have applied electric field and magnetic field, electric field cancels the magnetic field, so the charged particle does not undergoes influence under electric field and magnetic field. These two forces are cancelled. There is no force, so charged particle moves in a straight line path. Charged particle is undeflected. Undeflected means moves in a straight line. Straight line, moves in a straight line, moves in a straight line. Okay. Third case, maybe electric force is less than magnetic force. That means this time magnetic force is 10 Newton, electric force is 8 Newton. 8 Newtons cancels this 8 Newton and 2 Newton is left. Magnetic force is left. So magnetic influence will be charged particle in a circular path. So the charged particle moves in a small radius circular path. Okay, now is this clear? Charged particle in a circular path. Circular path. Here, parabola. But in velocity selector concept, the condition is magnetic force must be equal to electric force. Magnetic force must be equal to electric force. That means when electric field force is more, magnetic force is less, then how we will equate, how we will make these two are equal means electric field is strong, so you can reduce electric field so that electric force decreases, both becomes equal. This is one way. This is already more, so this is less, so you can increase magnetic field so that magnetic force increases, they will become equal. Velocity selector means magnetic force and electric force must be equal. Magnetic force and electric force must be equal and they must act in opposite direction. Opposite direction. Opposite direction. They should be in opposite direction. Then what will happen to Lorentz force? We'll see. I'll erase this. We'll see this. When these two are equal, net Lorentz force becomes 0. So this is minus QEB into J cap plus this is QE into J cap. If I take this side, I can write it as QEB is equal to QE. Both are J, so that's why I have removed. And the charged particle is same, so cancelled. So velocity with which the charged particle moving along the x-axis undeflected is V is equal to E by B. So this is how we are going to determine the velocity of the charged particle. When when they ask a question in the competitive examination, we have applied electric field and magnetic fields of certain strength perpendicular to each other, then a charged particle is thrown perpendicular to both electric and magnetic fields. It is undeflected. Then what is its velocity? If they ask, then the formula is V is equal to E by B. Okay? By using this concept, we can determine the velocity of the charged particle. Velocity selector is a concept can be used only when electric field and magnetic field and charged particle velocity must be mutually perpendicular. When they are mutually perpendicular, electric force cancels the magnetic force, then the charged particle moves in a straight line path undeflected in the presence of electric and magnetic fields. That's all.